In this paper, we present FlexISP, a flexible camera image processing framework. Our method can be applied to both regular imaging sensors and novel sensor designs. It takes in raw sensor data generated by an imaging system and produces optimized images in a range of output formats. FlexISP models and optimizes across multiple image processing modules to preserve the highest image quality. The conventional image processing pipeline is modular, and it takes in, for example, a Bayer image and sequentially applies demosaicing, denoising, tone mapping, and JPEG compression. It optimizes each module independently for its quality and performance. However, the conventional approach suffers due to the accumulation of error in each stage of the pipeline. Also, for novel sensor designs, the pipeline needs to be altered significantly. Instead, we collapse the entire image processing pipeline into a single framework. We model each module of the pipeline and combine all of the modules into a joint cost function designed for the final image quality. We ensure the fidelity of the data is maintained in the reconstructed image by comparing it to the original captured data in each iteration. Here we show the general form of the optimization cost function. We use a forward-backward splitting method to optimize the data term and the priors in our optimization. The data term enforces the relationship between the captured image data and the desired final result. The image priors are necessary to overcome the underdetermined nature of the imaging problem. Here is a total variation prior. Here is a denoising prior. Here is a cross-channel prior to enforce edge consistency across all channels. FlexISP handles a range of applications from demosaicing to multi-frame reconstruction for both old and novel sensor designs. Next, we present results of experiments with our framework. We begin with demosaicing the RGB Bayer sensor pattern. The system matrix A is simply the Bayer pattern with one color per pixel. Our method is better than the state-of-the-art LDI-NAT demosaicing method. Notice that the edges of the glass pane are smoothly reconstructed by our solution. LDI-NAT introduces zipper artifacts. Likewise, on the shirt, the paint strokes are smoothly reconstructed by our method. Next, we consider low light burst imaging using a regular Bayer sensor. The raw images are first registered and then combined. Here the system matrix A incorporates both the registration warp between frames and the Bayer sampling pattern. We perform both demosaicing and denoising on the captured burst raw images in a single framework. Our method is significantly sharper than the accumulation of the stack. Notice the sharp patterns on the dress and clean edges on the face. Next, we apply our method on an interlaced HDR sensor. The alternate exposures capture the dynamic range in a single frame, reducing ghosting artifacts. Here, the system matrix A incorporates the different exposures in addition to the regular Bayer pattern. Additionally, we mask out the saturated pixels and the noisy dark pixels where the data is unreliable. Here is an example of a captured interlaced HDR image. Notice the interlaced exposure in the captured image. Despite the saturated and dark pixels, we reconstruct the bench and its shadow sharply. Notice the detail preserved in the vase and the bushes behind the bench. Here is another example. The sand and the rocks in the shadows retain their sharpness. Finally, we compare with the standard exposure fusion. Exposure fusion causes ghosting in moving regions. We reconstruct the same scene with no ghosting while preserving detail in shadows and bright regions. Finally, we apply our optimization to fuse images captured by a 2x2 color array camera. We first estimate the cross-channel optical flow to warp different color cameras to the green color camera. Here, the data matrix A incorporates the optical flow warp. Here is an example of a scene captured by a 2x2 color array. A naive fusion of the color cameras results in significant color bleeding due to poor registration and occlusions across views. The cross-channel prior in our optimization enforces the edge consistency across color channels and eliminates artifacts. Our method runs efficiently on a GPU. The live feed on the monitor shows real-time reconstruction of 2 megapixel images at 15 frames per second. We also compute an HDR video from an interlaced HDR video feed at interactive frame rates. Notice the detail in the shadow regions. The low-light images are fused in real time to create a noise-free, demosaicked image. Please refer to our paper and supplemental materials for more examples. In conclusion, FlexISP solves a range of image processing problems under the same framework. Our method is efficient and adapts to a variety of sensor designs.